All right, we come to this slide here, which just gives some initial results from an early stage in the project, looking at the either the so-called efficiency or the execution time as a function of number of cores or the number of the size of the problem. Efficiency is a measure of the effectiveness in using multiple cores. These jobs are run from 64 to 192 cores, as you can see from the label at the bottom here. Number of cores here, 164 to 192. And 90% efficiency means that if you run with, say, 100 cores, you get, instead of getting 100 times the performance of one core, you get 90 times the performance of one core. And typically, you will find that the larger the problem, the bigger your efficiency. This is a feature of parallel computing that we'll discuss in general in a later lesson group. And these are just 3 different bioinformatics problems. They're each effectively, pleasingly parallel, namely each group of data runs independently, and the results are actually written out independently, and there's no significant reduction operation. And it compares multiple things. Here we have a triad link, which is Microsoft's version of MapReduce. Originally came from what the Bing group, the Microsoft search engine, developed for their information retrieval. So it is their implementation of MapReduce. It's a very nice, elegant technology, but as the world somehow associated MapReduce with Hadoop, Microsoft decided to switch from supporting Triad for general use. I think they still use Triad within internally to Bing. They switched to using Hadoop. And so we have Triad, Hadoop, Twister for Azure. There is appears that at this time Twister for Azure and Triad ran better than Hadoop, but that's not a very big effect. Here we have Hadoop. Here we have Amazon, and here we have Twister for Azure. So these 2 things are querying Twister running on the Microsoft cloud, Twister running on the Amazon cloud. The Amazon cloud just looks like the traditional non-cloud operation on high-performance computing, except it's implemented on top of virtual machines. And we have a similar comparison here for a different program called CAP3, which is an assembly program. And you can see the exact relative performance of the different codes varies from plot to plot. Twister does quite well. It's near the top in all these plots. Now we come to another example of data analytics. I've mentioned this data analytics, although currently we don't have a lesson group on it. Multidimensional scaling is a technology used to do dimension reduction, and it ends up being dominated by matrix or matrix vector multiplication. This is has a well-known parallel algorithm, which when implemented looks like iterative MapReduce. And we're comparing then our Twister running on a high-performance computing Linux cluster with Twister for Azure running on Azure. There is actually a 50 reasonably big effect, over a factor of 2, because the Azure nodes are actually slower than the Linux nodes that we're using. So you can look at the performance of the sequential code and remove that effect, which takes the blue curve, which is the raw Twister for Azure time, and then you convert it to the green curve. So that shows actually that in terms of parallelism, Twister for Azure is doing fine. And of course, the cost for the node is the cost. I mean, the speed of the node corresponds to the cost for the node, and it just says that. So the actual difference in node performance is not that important because you would just pay less for a slower node. And here we have a plot against with different size problems running on different numbers of cores. And here we have a plot which just compares the performance on a fixed number of cores as the number of data points increases. And again, we adjust for the sequential performance difference. In this plot here, we come to look at Kmeans, which we did in the last lesson group. And again, we have actually to do some adjustment because Hadoop is running on Linux. And therefore, instead of actually adjusting Linux, Azure, we adjust Linux because most of our plots here are the Azure plots. And here's the Hadoop plot running on Linux on Kmeans. This particular plot was meant to discuss different technologies for doing the collective operations. I pointed out that there are different ways of doing collectives. There's a lot of research in that area. And these are three different technologies. Here's the original one, and here's some improvements that have been recently introduced, showing better performance by just using optimized implementations of collectives. And here we have the final graph of this lesson group, which shows the results in terms of efficiency. Again, we have to adjust the Hadoop, and here we have the legacy version of efficiency of the legacy version of Twister, the original Twister for Azure. And here we have the efficiency, which is clearly much improved for the Twister for Azure with the new collective operations. And we have, it's not important for this particular discussion exactly what the improvement was. You'd have to look at the research papers to do that. And here's formally the definition of efficiency. Usually efficiency you think of as referring to the one core result, but there's so much data here it doesn't actually run on one core, so the smallest number of cores used is 32 nodes, which is why it's called relative efficiency. And this is the formal definition for this case of relative efficiency. The time on 32 cores times 32 divided by the time on n cores multiplied by n. And this again shows that Iterative MapReduce with on Azure is running quite well. So I expect to see lots and lots more work on MapReduce. Hadoop is really going great guns. There are many different iterative MapReduce technologies. This is not the place to go into for them. Into them, there's a very important one developed by Berkeley called Spark. Hadoop coming from the University of Washington. And there will be a lot of work and a lot of study in this area. And the net result will be very powerful ways of using clouds to do this type of parallel data analytics, which we've given two examples here of non-trivial iterative MapReduce, K-means, and multidimensional scaling, which have actually rather different operations. K-means is this, the critical thing is the calculation of the centroids, and the for multidimensional scaling, the key thing is parallel matrix multiplication. And so the next set of slides is discussing the performance of K-means using MapReduce. Thank you very much.